this lesson, we are going to discuss image formation in concave lenses through ray diagramming. At the end of this video lesson, you should be able to predict the qualitative characteristics of images formed by concave lenses through ray diagramming and identify some practical uses of concave lenses. From our previous video lesson, we learned that concave lenses are also called diverging lenses. A unique feature of concave lenses is that the ends tend to separate, which make them thicker at the ends. Concave lenses, just like convex mirrors, only produce one type of image. But how do concave lenses form images? Let us now discuss the image formation in concave lenses using ray diagramming. In ray diagramming in lenses, our goal is to describe the qualitative characteristics of the images. Thus, we have our LUTs or the location, orientation, type, and size of the image. We have here our diagram containing all the points. For this diagram, we are going to predict the qualitative characteristics of the image formed by an object placed in between two f(1) and f(1) of a diverging or concave lens. Thus, the object distance d sub O is less than 2 f(1) but is greater than f(1). There are 3 rays for ray diagramming in lenses. But again, 2 rays will already work. First, we have the principal ray. It will be drawn from the tip of the object, then incident to the lens but in the direction which is parallel to the principal axis. Since this is a lens, the light should refract. It would refract away from the lens but with respect to f(1). Thus, we draw an imaginary line as a guide from f(1) to the point where the incident principal ray reached the lens. From this, we now draw the refracted principal ray. For the second ray, we have the focal ray. The incident focal ray should reach the lens with respect to f(2). To properly draw this, we first draw an imaginary segment from the tip of the object going to f(2). Second, we can now draw the incident ray from the tip of the object going to the lens. For the refracted focal ray, we draw a ray going away from the lens but parallel to the principal axis. Lastly, let us draw the central ray. Simply draw a ray from the tip of the object passing exactly through the optical center of the lens. This ray will not show any refraction. As we can see from this diagram, only the guide of the refracted ray and the central ray have intersected. We can already consider this as our point of intersection, but we can still check its accuracy by extending the refracted focal ray. Now that the 3 refracted rays have intersected, we are sure that this is the location of the image. We can now describe the image. For the location, the image is formed in between f(1) and P. Write it as d sub I is less than f(1) but greater than P even if f(1) is negative. The negative sign of f(1) is just used to denote that the lens is diverging. But taking into consideration the distance of f(1), it is still farther to the optical distance compared to the image. Next, for the orientation, since the image is formed above the principal axis, the same with the object, it is upright. Automatically, this is virtual. Another explanation for this is that it is formed on the side of the lens with the object. Lastly, the size is reduced since the image is smaller than the object. So these are the image formation and qualitative characteristics of images formed by objects in between two f(1) and f(1) of a diverging lens. But what if the object is placed in between P and f(1)? Let us do the 3 rays for this diagram. First, we have the principal ray. It will be drawn from the tip of the object then incident to the lens, but in a direction which is parallel to the principal axis. It would then refract away from the lens but with respect to f(1). Thus, we draw an imaginary line as a guide from f(1) to the point where the incident principal ray reached the lens. From this, we now draw the refracted principal ray. For the second ray, we have the focal ray. The incident focal ray should reach the lens with respect to f(2). We first draw an imaginary segment from the tip of the object going to f(2). Second, we can now draw the incident ray from the tip of the object going to the lens. For the refracted focal ray, We draw a ray going away from the lens but parallel to the principal axis. Lastly, let us draw the central ray. Simply draw a ray from the tip of the object passing exactly through the optical center of the lens. This ray will not show any refraction. Just like in the previous diagram, we are going to extend the refracted rays. And this is where the image is formed. As we can see in our diagram, the image formed here has the same qualitative characteristics with that of the image formed by an object in between f(1) and 2f(1). This means that for any object positioned in front of a diverging lens, the image will always be in between f(1) and the optical center, upright, virtual, and reduced. Diverging lenses are commonly used in door viewers or peepholes. Peepholes or door viewers are security devices that give a panoramic view of objects outside walls or doors. A concave lens is used to minimize the proportions of the objects and gives a wider view of the object or area. Another function of concave lenses is the correction for nearsightedness. Concave lenses are most widely used to correct myopia, which is also known as nearsightedness. The eyeball of the person who has myopia is too long, and the images of distant objects fall short of the retina. Concave lenses are also used in glasses that correct the disparity by scattering the light rays until they enter the eyeball. This allows a person to see things far away more clearly. To summarize this lesson, let us review the following key points. Concave lenses or diverging lenses are lenses that are thicker at the ends. The three rays used in diagramming image formation in concave lenses are the principal ray, focal ray, and the central ray. And lastly, concave lenses always form virtual, upright, and reduced images formed in between P and f(1) of the lens. And that ends our discussion on image formation in concave lenses through ray diagramming.